Alright, welcome to another AQA's chemistry video. Today I'm going to be doing a video on shapes of molecules. So this topic will come up mostly, this is a very important topic in terms of the fact that it always comes up in the exam. Pretty much nearly always, and you just ask a simple question of what is the shape of this molecule? What is, how would you describe the shape of this molecule? That's the type of question that they would ask in your exam. And it's a very easy thing to do, but people kind of I've seen maybe some teachers or maybe some videos online where people kind of overcomplicate, and it's actually a very simple way of doing it. Shout out to Allery Chemistry. As just the channel that I watched it when I was doing my A-levels, and he actually explained it very easy. I did it kind of slightly differently, but more or less similar to the way he did it, really. Yeah, that's it. And this kind of topic there's like this transition metals in year 2 where this topic kind of comes up. So you need to have a good understanding of this topic, right? So, okay, I'll stop talking and get straight into it. So, valence shell electron pair repulsion theory. So, VESPR, it's also known as VESPR, helps to explain the molecule's shape by considering electron pair repulsion. So, why is that there? Charge clouds, right? So, electrons occupy orbitals, but what is an orbital? Because we always talk about, my last video, a couple of videos ago, I made a video on electron configuration. I'll leave a link in the description to that video. But we talk about electrons occupying these orbitals. What actually is an orbital? An orbital is just a region of space where you're likely to find an electron. The usual definition is that an orbital is a region of space where there's 95% probability that an electron is located, meaning that you can view electrons not as particles but as charge clouds or regions of space where an electron is located. So think about, this is how a charge cloud, like for example, I was writing a lone pair. You can also draw lone pairs like this, where it's like, you know what? Yes. Did I allow that? Think of electrons. That's how you can draw a lone pair, right? Think of electrons more like this. So they're not fixed in place. They're more like they're in a cloud of space. They occupy a region, right? Like when we talk about like even bonding was to an extent they when we talk about this, right? We talk about like the electrons being like this, right? But they're not completely fixed in place. They just occupy this space. They're very likely to be found in this kind of like a region, pi bonds, sigma bonds. But like the idea is that the electrons aren't completely stationary. They're still kind of moving. They're still moving around. But there's a 95% probability that you'll find an electron within this region here. Of course, movement of these subatomic particles is random. It is random. That's a known fact. However, you do know there's a 95% probability that it'll be somewhere within this region here, right? So repulsion, right? So these two things, charge clouds and repulsion, are linked to the shapes of a molecule. So let's go on to repulsion now. So electrons are negatively charged, and they repel each other. So electrons will try to stay as far apart from one another as possible, hence determining the geometry of a molecule. The electrons in the bonds repel and try to stay as far apart from each other as possible. So this is quite a quick key thing, and sometimes they ask you in exams why it takes that shape, or why if you find, for example, one of the compounds, one of the shapes, for example, something called linear, and if they say why does it take that shape, why is it in that arrangement, or why is it in that geometry, you say it's because it's done in this way because the bonding pairs for example, or the lone pairs are as far apart from each other as possible to accommodate that type of geometry. I'll show you an example of a compound. This kind of repulsion idea is more clear to see, but the idea is that molecules take up a specific geometry because of these charge clouds and the way that these charge clouds repel each other and the repulsion of these bonding pairs and lone pairs. So it makes sure that they can be as far apart from one another as possible to maintain a stable shape. All right, lone pairs and bonding pairs. So an important detail is differentiating between the repulsion of lone pairs and bonding pairs of electrons. So lone pairs are held closer to the nucleus of an atom, meaning that they repel each other more as they're physically closer. So when you're talking about these kind of lone pairs here, right, they're much closer to the nucleus, or most close to the central atom's nucleus compared to these bonding pairs. So I was thinking about, kind of give you a kind of idea. It's like this isn't an actual molecule, but I'm just trying to show you an example, right? Imagine lone pairs being like this, and then bonding pairs, let's just say there's a hydrogen here, they're kind of like this, right? Actually, other way around. You know what I mean? So it's like these lone pairs are much closer to the nucleus of the atom compared to the bonding pairs. So they repel each, because they're much closer to one another, they repel each other much more than bonding pairs. And the trend in repulsion strength from most repulsion to least repulsion from 1 to 3, lone pairs repel lone pairs the most, then lone pairs repel bonding pairs the most, and then bonding pairs repel bonding pairs the least. So these bonding pairs would repel each other the least because they're usually the furthest apart from one another. They still repel, but it's not actually that strong compared to lone pairs repelling lone pairs or lone pairs repelling bonding pairs. And that's the trend in repulsion there. So electron pair repulsion, so electron pairs and geometry. There's an optimum geometry for every number of electron pairs, and the different types of geometries can be represented below. So I'll show you the names of them, the linears and all that, but first of all, we need to understand how do you actually, how can I tell the shape it has, right? This is the important thing. This is how where the question is. They'll ask you a question where they'll give you a compound and say, what geometry, what shape is this compound, right? If they can give you any example, what geometry does this, or what they'll say what shape is this compound, what shape is this so and so compound, right? And the way you do it is there's a lot of different examples of how people do it, right? And it's kind of like, but this is how I do it at least, and this is how it worked for me. I draw the dot and cross diagram, and then when I draw the dot cross diagram, if you have molecular compounds or molecular ions, it's a slightly different thing. I'll go on to that later. But the first thing to do, draw the dot and cross diagram. The second thing I do is I'll see how many bonding pairs and lone pairs I have based off that dot and cross diagram, and then I'll sum up the bonding pairs and lone pairs. This part isn't a real intensive step that you have to like do in terms of understanding the compound, but this is useful because it's kind of like a cheat code. This step 3 is kind of like a cheat code because if you sum up your bonding pairs and lone pairs to see how much electron pairs you have in total, that you can kind of already tell what kind of compound it is, even if it has even if it has a lone pairs in it. You can kind of tell the shape of the molecule if they're within a certain number of electron pairs. When I do an example, this will all makes much more sense to you. But right, so but draw the total cross diagram, see how many bonding pairs and lone pairs you have, add them all together. You can work out the shape and then make any adjustments if you have any lone pairs, right? So let's see linear. Linear is one of the types of shapes. Right? It's the most basic type of geometry. So central atoms of a molecule has 2 electron pairs. It will likely adopt a linear geometry and a bond angle of 180 degrees. So when I mean 2 electron pairs, is this step 3 here. It's a sum of 2 electron pairs, and that's because there's 2 bonding pairs and no lone pairs. So in total 2 plus 0, that's, if I add it together, 2 bonding pairs, 0 lone pairs, 3 electron pairs together. I'll go more to this step 3 a bit later, but just understanding this 1, 2, 4, and 5 like are the main points, right? So I've supposed to do the dot and cross diagram of carbon dioxide. You should already know this one already. That's a terrible cross there. Yeah, you already know there's only 2 bonding pairs and 0 lone pairs. So how I would represent this is as this. Of course, there's technically 4 bonding pairs. I should probably say 4 bonding pairs, but like in terms of where it bonds to, it's bonding to the same atom. So there's only 2 bonding pairs in terms of the fact that it's bonding one to oxygen and one to another oxygen. Obviously, triple bonds, whatever. But I'm talking about how many times the central atom is bonding to another atom. Alright, so this is described as having a linear geometry, and the bond angle between the bonding pairs is 180 degrees. Alright, let's go to trigonoplanar. If a central atom of a molecule has 3 electron pairs, it will likely adopt a trigonoplanar geometry. The bond angle is 120 degrees, and there's 3 bonding pairs and no lone pairs. So I mean with 3 electron pairs, right? So if I was to use, let's say boron trifluoride, right? Boron trifluoride, or BF3. It's the dot across that. Boron is in group 3, so, and fluorine group 7. You see here, so that there's no lone pairs, just 1, 2, 3 electrons for boron, and then each electron for fluorine, and enough. That's enough to say it's 3 bonding pairs and no lone pairs. And this shape is called trigonal planar. You see, it's a triangle or tri, kind of like free, and it's planar. It's all within the same plane, and the bond angle is 120 degrees. When you hear the word planar, you can think of a 2D kind of all within the same plane. So it's 2D. So you can think of the angles being within 120 degrees. So you think of them all being within 360 degrees. And since there's 3 of them in the same plane, equally the same far. Sorry, I can't speak today. If they're all within the same plane, right, and it's 360 degrees, that means, and there's 3 of them, that's split by 3. 360 divided by 3, that's 120 degrees. And that's why it can be, we know it's 120 degrees, right? The next example doesn't follow this principle. So next one is tetrahedral. So if a central atom of a molecule has 4 electron pairs, it will likely adopt a tetrahedral geometry. And the bond angle of this is actually 109.5 degrees. And I explain why, right? So it has 4 bonding pairs. I'm using an example, 4 bonding pairs and no lone pairs. Right. So with this example of a tetrahedral compound here, let's say methane, right? So we all think of methane, when we think about methane, right? The reason why it's different to this one here, right, is because it has, when we think about methane from organic chemistry, we think of it like this. We draw it out like this in organic chemistry. It does not look like this in the actual atom. The actual molecule doesn't look like this. The reason for it is that they're not fixed in shape. It's not like a carbon-carbon double bond where it's like it's fixed, rigid in shape, all within the same plane. No, these hydrogen atoms are not in the same plane. They're not in the same plane. Whereas with trigonal planar, all the fluoride atoms were in the same plane as boron, so it could be described as being a planar shape. So therefore, when you think about methane, right, we do our dot and cross diagram, as we said before, we follow that rule. Draw the dot and cross diagram. If you don't need to, if you already know it, then it's not going to be a problem for you. But just for the sake of, if you don't know the number of bonding pairs and lone pairs, carbon's in group 4, so that's four electrons in its outer shell, and then each hydrogen would donate its own hydrogen. This is a very unclear diagram. Let me make it a bit bigger. Right? It's not that big. So carbon has 4 electrons in the outermost shell, and it donates, and then each hydrogen donates its own electron, completes that. There's 4 bonding pairs and no lone pairs. And it's actually represented like this. You have the central carbon atom here, and you have a hydrogen atom here, and there'll be another hydrogen atom on the same plane here. But then the other 2 carbon atoms, so the other 2 hydrogen atoms are not on the same plane. So we do our wedge diagrams that are, we have one called a wedge that's kind of coming towards you, it's a solid line. So we represent any hydrogen atom, this is coming towards you in the plane. Sorry, do another example. We draw a solid line, and this is show that the hydrogen atom is coming towards us. And we do another kind of broken line, we call it. And that's show that the hydrogen atom is going away from us. So I haven't got the best things here to show you it, but imagine that was our, this is the central carbon atom here, that's a hydrogen, that's a hydrogen. These will all be on the same plane, right? These are through the same plane. When I see this line is coming towards you, it's a 3D shape where this is actually pointing towards you. It's kind of like coming towards you, and this kind of broken back line here, it will be kind of represented by dashed lines. That's going away from you. So it's a 3D object that's kind of going away from you. So that's how it look like in 3D. So that's your, these are in the same plane, and you have one that's coming out towards you here. Imagine that as a 3D shape. I know this probably isn't the best example of it, but I wish I had like some, if you ask your teacher about getting a molly-mod example, that's probably a better example of it. But the idea that a 3D shape, this one's coming towards you, that hydrogen's going away from you, same plane, right? All right. Trigonal, and then sorry, the bond angle between each one, because it's not on this, they're not 3D shaped. We can't say it's not out, the bond angle isn't out of 360 degrees. So the actual bond angle between each one is actually 109.5 degrees. Don't ask me how I'll explain. You don't need to know how I'll explain, but it's just knowing that it's not in the same, they're not on the same plane. So it's actually 109.5 degrees in this example here. And this, because it's this angle because it allows for all the bonding pairs are as far apart from each other as possible. You know, all the bonding pairs are repelled as far apart from one another as possible. If they ever ask you why it's 109.5 degrees, it's because this angle allows the bonding pairs to be repelled as far apart from one another as possible to accommodate this geometry. All right. Next one is trigonal bipyramidal. There's a lot of it. I always thought when I was studying, this is a lot of shapes you need to remember. But you know, when you've got to like end of year 13, it's not actually that bad. So trigonal bipyramidal. It's have I got any examples of trigonal bipyramidal? Yeah, I have actually got an example of triggers. But anyways, it's a central atom with 5 electron pairs. There are 2 different bond angles. One is 120 degrees angle around the equator. One is a 90 angle from the equator to the apex. And I'll show you what I mean by that. So let's say PCl5. So phosphorus, chloro, and 5 chloride. PCl5, right? Phosphorus is in group 5. And each chlorine, 1, 2, 3, 4, and a 5th one here. Right. So how would they actually represent this compound, right? We have our central, we know there's 5 bonding pairs, right? 5 bonding pairs. No lone pairs. And that's a total of 5 electron pairs. 5 electron pairs usually is a trigonal bipyramidal structure, and it has this shape here where you would have the chlorine here. The ones that are in line, this is how it's represented here. Chlorine, these are on the same plane, and then you have one here is also on the same plane, but you'd have one that's kind of pointing outwards, one going away from the plane, so a dashed line going out of plane, and a wedged line that's coming towards you, or it's in front of or it's described as being in front of the plane. Right, and so this angle here, so we said we have 190 degrees from the equator to the apex. The apex is usually between the top or the bottom, or the, you know, I guess either one of them could be the bottom, whichever way you flip it around. But apex usually regards to the peaks from a center point, right? Apex of the heart is bottom of the heart. Anyway, so this angle here is actually 90 degrees. This is a right angle from here to here, but then the other angles is 120 degrees. So 120 degrees, 120 degrees, 120 degrees. Before you ask why, that's clearly not 120 degrees. Remember, these are not on the same plane. It looks like this is like kind of like they're all in line with one another like that. It's not. One is actually going like from just imagine this kind of like going from here to here, like this, like from here to here is like kind of like going from that angle. I just shown it so you can see it, but really this from here to here to here to here is actually more like that. So there's 120 degrees bond angle between each of these. They're not. This is not a 3D. This is not a 2D molecule. This is a 3D molecule, because different, not on the same plane, right? And that's what. And this is described as being trigonal bipyramidal. It's kind of looks like it has three. From an example, it looks like it has three pyramids on it. I wish I had a modeling more so you can see it from a certain angle, but this is kind of like a pyramid here between this and here. That's a kind of like a pyramid. It looks more like that. A pyramid between these three here, and a pyramid between this, and that. So that's why it's described as being trigonal, bipyramidal, or I guess two pyramids. Three is three. It's more like two pyramids to be honest. But the idea is three. But yeah, you can clearly see I'm not very good at explaining things. Octahedral. Right, last one. Central atom of molecule has 6 electron pairs. Central atom of a molecule has 6 electron pairs. The bond angle will be 90 degrees. So, so 6 bonding pairs. No, or 0 lone pairs. The example I'm going to use is SCl6. So sulfur and SCl6. Can I get one? Oh, I'll do it here. SCl6. 1, 2, 3, 4, 5, and that's actually terrible. Good. So that's the dot and cross diagram. Happy with that. What it actually looks like, right? Octahedral shape is so each one has a bond angle of 90 degrees. Cl, one's going is symmetrical on all sides. So Cl here. Cl here. Cl here. Great, right? So that's what it looks like, right? And it's, if you, I remember these are not on the same plane. I say it all the time here, but just making sure that you get that, because the way you can show it's on the same plane, the way you show it's 3D, is by drawing this. I should probably kind of like make it clear this is a wedge. Kind of like scribble it in a bit more. By doing the wedges, you're showing that it's 3D, and you will miss out on marks if you just represented it all by one line or a seal. If you give all these bonds by one line, you're kind of giving the impression that all on the same plane, and you won't get the marks from it. It's important that you show the wedge lines, and that's to give that the idea to the examiner. You understand it's a 3D molecule, and hence why its bond angles are all 90 degrees. Because if you actually looked at this compound, it would look like a 90-degree compound. I wish I got the pictures of it, but it is a 90-degree compound. if you want to look it up online. But yeah, that's what a octahedral shape looks like. Lone pairs. So for every additional bonding pair, the bond angle decreases by 2.5 degrees. So I've done examples here with no lone pairs. But I'm going to show you where it is with lone pairs. I'm going to explain this point here that I had above with the adding them together and what they kind of look like, right? So for every additional bonding pair, bond angle decreases by 2.5 degrees. Why did I say Celsius? It's not temperature. For example, if the bond angle was originally meant to be 109.5 degrees, it's now 107 degrees. And if there's two bonding pairs, it will be 104.5 degrees. So the idea is every lone pair that you add is the bonding pairs get repelled. Remember, lone pairs repel bonding pairs more. So for every lone pair you add, the bonding pair angles, the angle between bonding pairs would decrease by 2.5 degrees. So the first one I'm going to go through is bent. So if a central atom of a molecule has 3 electron pairs and 2 bonding pairs, and lots of that's 2 bonding, so 3 electron pairs, and that's 2 bonding pairs and 1 lone pair in total. If you add that together, it will adopt a bent geometry. This geometry is similar to the trigonal planar geometry, as it's the same total number of electron pair numbers. So I'll show you what I mean. So a bent example. I haven't got an example of a bent geometry. Right, I haven't got an example of a bent geometry, but let's just say, Let me get so the first one is bent. So if a central atom of a molecule has 3 electrons, 3 electron pairs, so it has 2 bonding pairs and 1 lone pair, it'll adopt a bent geometry. And this geometry is similar to trigonal planar geometry, as they share the same total electron pair number. So what I meant by that is that, as you can see here, 3 electron pairs, it only has 2 bonding pairs. But if you sum the 2 bonding pairs plus the 1 lone pair, it has 3 electron pairs in total. And when I actually show you this geometry, it looks similar to trigonal planar. And I'll show you what I mean. So SO2, right? Let's draw the dot and cross diagram of SO2. SO2 has, so, what's that? Is that one? Yeah. If I get oxygen here, another oxygen here, we know that it shares 2. But silver has 2, so it has 2 more electrons there, and that forms a lone pair of electrons. So 2, 4, 6, oxygen here, and how it will be represented, it'll be having your central atom here, your sulfur, your 2, and you'll have the lone pair up here. This will probably be, this is 177.5 degrees technically. If you're decreasing it by 2.5 degrees, the bond angle is now gone down from 180 to 177.5 degrees. Right? But the idea is that it's probably not even a good example of a lone pair. But I want to draw like. Is that better? Yeah, I like that better. Right. The idea that this lone pair here causes stronger repulsion to bonding pairs than bonding pair repulsion. Because you see before, when you have this, like when I had the first example here of the of linear, right? The bonding pairs in order for the bonding pairs to be repelled as far away from each other as possible, for these to be as far away from each other as possible, they have to be 180 degrees from one another. Because there's no lone pair, but that lone pair has such strong repulsion. It has a repulsion that's kind of similar to trigonal planar, in terms of it has this kind of shape in a way. That's what I mean. So three electron pairs in total, kind of has a similar shape. But I'll show you another example to emphasize my point. Right? Let's go for trigonal pyramidal. If the central atom has 4 electron pairs, so 3 bonding pairs and 1 lone pair, it'll adopt a trigonal planar geometry. Right, so 4 electron pairs. Let's see what I had for 4 electron pairs up here. It was tetrahedral, right? It will share a structure that's actually very similar to tetrahedral. I'll show you an example. I'll show you how to do NH3. So if we're doing ammonia, so it will be nitrogen here, so that's 3, so 1, 2, 3, 4, 5. In terms of the, actually, you know what, let me make it a bit more clear for you. One, two, and 3 from the hydrogen. The hydrogens will give 1, but 1 from nitrogen, that's the hydrogen there. 2 sorry, 1 from nitrogen, that's 1 from hydrogen there. 2 from nitrogen, that's 1 from the hydrogen there. 3 from nitrogen, that's 1 from the hydrogen there. And then 4, 5, right? Because nitrogen's on group 5. That's 1 lone pair, 3 bonding pairs. How to represent this? We have our nitrogen here. You'd think if it just had 3 bonding pairs, it'd be trigonal planar, right? But it's not. We have a electron pair. So I represent the. That's a terrible. I used to be excellent at drawing these. Yes, bonding pair here. And then I would write. They're not all on the same plane. 1 that's on the same plane. This is coming towards you on the plane. Hydrogen here. Hydrogen here. And this is considered to be trigonal, pyramid, or trigonal, and it's kind of like a pyramid shape here, because actually, if you were to do it to be like a pyramid shape, right, on the bottom is forming here. Right, it's forming the 3 hydrogen on there and then the nitrogen here, and this lone pair is so strong that it's able to repel all 3 of the bonding pairs here. That's what's happening, and that's why it says it has a similar shape to the bond. The total number of electron pairs kind of all have a similar shape, and this kind of looks like a tetrahedral shape. It looks kind of similar to that tetrahedral shape that we had before, right? So that's etc. etc. So here's a table. I could go through all of them. I'm not going to go through every single one of them, but here's this table showing the shapes of molecules with their steric number, which is just the total number of electron pairs, and their respective number of bonding pairs and lone pairs. So here's every single example. So if I was to have 0 lone pairs, just the ones I got over before: linear, trigonal planar, tetrahedral, trigonal bipyramidal, octahedral. And if I have 1 lone pair, bent or angular, trigonal pyramidal. There's for trigonal bipyramidal, if it has 1 lone pair, but it has 4 bonding pairs, 1 lone pair. You see trigonal bipyramidal and seesaw. It's called seesaw, right? The reason why it's called seesaw, kind of looks like a seesaw from if I was to change this, I wish I could angle it, right? But if you're looking at it from this angle, it looks like this is the pivot for the seesaw, and this kind of goes up and down from each side of the seesaw, right? That's why it looks like seesaw, bro. And then square pyramidal, you see how this, these are different. This is 5 bonding pairs and 1 lone pair, but can you see the similarity in the shape, right? And if I had 4 bonding pairs, 2 lone pairs, the steric number, when you have the same steric number, it doesn't matter the number of lone pairs, the shape is roughly the same. Not exactly the same, but roughly the same. And that's what you need to get an idea. So here's an example, right? What is the shape of a water molecule? Pause the video now and try and answer the question. All right, so let's do this example. So I know these off by heart because I've done my exams already, but for the sake of the fact that you need to know this off by heart, right? You're never really gonna fully ask for like these ones here, but it's usually up until they might ask for that, but it's usually these that they want, or kind of like here. They never really go for 3 lone pairs, 4 lone pairs, and they probably help you out for that. But you need to off by heart. You need to know these. You need to at least know these shapes here, right? So water molecule, right? So let's just do that. If you didn't know, that would be hydrogen there, and then another hydrogen here, but it has oxygens in group 6, so it has 6 electrons on the outermost shell, so it's sharing one with this hydrogen here, 2, 3, 4, 5, 6. So that's 4 electron pairs in total, but that's 2 bonding pairs, 2 bonding pairs, 2 lone pairs. How does I represent this? Right, so we know for, if you guys didn't know how to do this one here, yeah, it's here for you. You'll try and do it with this one first, and then over time you'll learn. So 2 bonding pairs, 2 two bonding pairs, 2 lone pairs, right? So that's 4. The circuit number would be 4. It's 2 and 2 together, 4, right? I already know it's bent because I've done this question a lot, but in case you know, it's bent, right? Because it's got 2 lone pairs and 2 bonding pairs here. How do I write this out? This question comes up. This one, if it ever comes up, just know it's quite an easy one to do. I always do this. You don't have to represent your lone pairs like this. I think you can get away with writing them, drawing them like that, but I always like showing the electron cloud. I just like, that's just me personally. They won't take away a mark from you drawing an electron cloud unless the electron cloud looks really ugly like that. There we go. Two lone pairs, 2 bonding pairs. But for molecular ions, this is the slight adjustment to the first step in the rule. Now remember when I said about all the way here, I said, let's go all the way back up to here, right? I said this the slight thing when you're talking about molecular ions, is a slight thing you need to adjust for, right? So it's when you're talking about molecular ions, where is it? There's a slight adjustment to the first step of the rule. When you're doing a dot and cross diagram, when you're doing positive ions or negative ions, you have to take away or add certain electrons in order for it to make sense. All right, and that's also because of the fact that the electron in that central atom is either being used or not used or taken away. It's either not part of the compound anymore, or it is being used. It's being gained from another atom, right? So when we're talking about positive ions, right? When drawing your dot and cross diagram, if it's a positive ion, you would remove an electron from the central atom, right? So let's do NH4, right? Ammonium and an ammonium salt, right? NH4. Ammonia, and so nitrogen is in group 5, so there's 5 electrons on its outermost shell. One, 2, 3, 4. That's 1 here, 2 here, so represent the hydrogens. 3, 4, and now it would be 5, right? If I was to write this, it would be 5. But that doesn't make it, can't have just one. It has to be, if it's a lone pair, it's a lone pair. It can't be a part lone pair. It has to be a full-on lone pair. So what I do is we'd remove one in order for it to make sense. And this is why, so now you just have 4 bonding pairs. And no lone pairs. I just write LP, 0 lone pairs, right? We already know what that is. That's just tetrahedral. Now, in the exam, they might take away a mark from you. They do allow it. They have allowed it in previous exams, and I'll show you what I mean here. You have to draw a bracket around this compound and then show the charge. They have allowed you in certain exams, but I feel like in the next coming exams, they won't allow it anymore. So obviously, and that's just to represent our structure there, right? Now, how I'd represent this here, bracket. I feel like at some point, they have allowed it, but I feel like at some point they will just say, no, we want you to write the brackets, right? So this is technically the correct way of representing, because it is a positively charged molecular ion. Now, if it's for a negative ion, when drawing a dot and cross diagram, you would add an electron to a central atom. So let's say IF4 minus, right? Iodo tetrafluoride. if that's the right name for it. If it's not, sorry. Same thing as usual. Actually, you know what? You do it. You try and do it. Now that you've seen what it's about, try and do this question yourself. Pause the video now and try and do it. I'm assuming that you've done it now, so. Ooh. Iodine group 7, so you'd actually gain an electron. So the central atom, you just do the full amount of electrons, right? When you're adding these side electrons, you're just doing the electrons and outermost, the electrons that you gain. So for fluoride, it would have to gain, it only really donate an extra electron. So fluorine, right? Because in group 7, you can only only gain an electron. But that's 1, 2, 3, 4, 5, 6. Sorry, 1, 2, 3, 4, 5, 6, 7. But because it's a negatively charged ion, we would gain another electron here, right? That is, so in total that's 4 bonding pairs. And 2 lone pairs. I would describe this compound as being, it has a steric number of 6, right? 6 as a total has a steric number of 6. So it should look kind of octahedral in some form of way. And I believe it is square planar. I think this compound is called square planar. How I would represent this, I here, the lone pair, a lone pair above, a lone pair below, fluorine here, make your one a bit neater than my one, I guess, but great. If I'm wrong, I'm going to double check just to make sure that it's the right one, but it should be, yes, and it's 90-degree angle between each one. See, it still kind of looks like kind of octahedral shape. So that's why. So if you're ever struggling to find out what kind of shape it is because of the lone pairs, add up your lone pairs together. Add up your lone pairs together. See, I forgot what this compound would actually be, but it's because I added my bonding pairs and my lone pairs together to get my steric number, which is the total number of electron pairs. I knew it kind of looked like a octahedral shape. So it's like, how can it look like an octahedral shape? So I have 4 here and I have a 2 here, so it must be 2 lone pairs on top, and I have my 4 bonding pairs on the side. But remember, this is 90 degrees; they're not on the same plane. And yeah, that's it. Hopefully this video was helpful. If not, then I guess tell me in the video, I guess.